All right, I'm going to go ahead and get started. And so the class is about design for manufacturability. And who's heard the term design for manufacturability before? So when you hear the term, what does it mean to you?
It means don't make pockets that aren't machinable.
All right, so you're thinking about machinability. When you hear it, what are you thinking of?
And it's manufacturability, it's not necessarily just machining.
Right.
It's also 3D printing and other forms of manufacturing. Same gist, don't design parts.
So don't design features that are going to be difficult to machine. Up in the back, is same idea? Anybody had heard anything else about it? Think about how you'd actually put it together. And so the most common topic when people talk about DFM or design for manufacturability or DFA, sometimes they call it, is most often people are thinking about design for assembly. So when you have, like if you bought a, I don't know, anybody ever bought a vacuum cleaner? Right? Have you ever taken apart a vacuum cleaner? Yeah, of course you have. And otherwise, why would you go to this school? Right? So you've bought a vacuum cleaner, you've taken a vacuum cleaner apart. Was it clearly designed to go together one way? Yeah, because they make a lot of those. And one of the big things, and it's really a tie-in for the lean manufacturing that we were talking about earlier in the week. One of the main big important things is you want to eliminate the possibility of errors, right? So if two parts have to fit together and it's only physically possible to put them together in one orientation, that's going to be better than if two parts have to fit together and you could put it together the wrong way. Unless putting it together the wrong way doesn't matter, right? So when we talk about DFA or DFM, that's often the thing that comes up. People have written books about it. You can get a master's degree or a PhD just in that. In how do you design stuff for mass manufacturing? And that makes a lot of sense because most of the stuff we use came from some mass manufacturing process, right? Most of the stuff that surrounds us every day came from some process that was making more than two pieces. But this design for manufacturability, I think, is especially important when you're doing like prototype design. When you're thinking about, so the part that I want, so the things that you're going to want for your MQP, the things that you're going to want one or two pieces of, if you can design them such that they can be made, then you're more likely to get them faster, be able to iterate faster, be able to use them sooner. And I see this all the time. Years ago, when I first took this job, I thought my job was to help students make things. And I spent a lot of time doing that. I would work 6 a.m. till midnight, 6 days a week, meeting with students. I'd schedule a meeting with you at 9 p.m. to go work on your parts and help you with your project. And it turns out that that's not sustainable. And that if you really looked at what my job was to develop systems to enable the students to make their own parts. My job wasn't to make the parts for the students. But it took me a while to figure that out. And while I was doing that, when I was doing my job wrong, I got to see a lot of people's designs very close up with detail. And then after that, when I was in industry running a small machine shop, I got to see people who have, so those were mostly people without degrees, right? People who are still learning. So I should cut you some slack. If you came to me with a design and it was poorly designed, well, hey, you came here to learn, not to already have been perfect, right? So I should cut you some slack. But then in industry, I would see the same kind of mistakes, except in industry, those mistakes could be more expensive. So we did a job once. It was 500 pieces was the total order. Nobody had ever made the part before in the world ever. Very difficult to machine part. It was a $200,000 purchase order. The first $25,000 was for delivery of the first part. So they're going to pay us $25,000 to make one piece, and then 500. I guess it was $500 a piece after that. So the first piece, $25,000. The next piece, $500, and then we keep doing that because the idea is you figure out that process that first time through. And so, and the workpiece material was not like readily available. You couldn't just go buy a new one if you broke the part. They had to. There was a whole process they used to make it. Our customer was the material manufacturer. Every time they turned on their system to make this material, it cost $100,000 to turn on the apparatus. It would take a couple weeks to make a batch, and then you only knew if the material was good after you started machining it. So you couldn't tell just by looking at it if it was any good. So it's not a cheap thing, right? So anyways, as we made each feature on the part, we would measure it to make sure we made it correctly. Yep.
What material?
It was crystal grown silicon carbide. So CVD SiC. It's hard. It's easy to make in thin coatings. So like your cutting tools and stuff will often be coated with stuff like this. Very easy to put down a thin coating of it. Very difficult to make a piece an inch thick. That's the problem, is as they build up layers, there could be cracks and stuff in between them. Anyways, so we'd make a feature, we'd measure it to make sure it met the drawing, right? We go through this process. About 2 weeks in, one feature left to make, and I'm looking at the drawing and I said, that tolerance doesn't really make sense to me. And if you're a good vendor to your customers, when something doesn't make sense, you reach out and ask them. You don't just make the part and ship it. And so it didn't make sense. I thought there might have been a mistake. And several emails and phone calls back and forth. And then somebody said, "What's the revision number on the drawing you have?" So I told him. And it wasn't the drawing for the right part. But they just paid me $25,000 to make the wrong part. Right? So, yeah, when it's a student that makes a mistake, you cut them some slack. Turns out when it's $1 billion customer that makes a mistake, you also cut them some slack and you do it again. But anyway, we often see this, and often see it with young engineers. And it's the young engineers that get tasked with the grunt work of doing the design that you're going to send off to manufacturing, especially on prototype parts. And so on the same theme of Tuesday, right? I want to say Monday's talk, but it was Tuesday that we met last. On the same theme of technobabble, buzzwords, lean manufacturing, if you know how to talk to the cranky old machinist and you ask them for some advice as you're working on your project, you're likely to get a better design in the end, and they're likely to help you. So I want to just start off with these 5 things that you need to know before you talk to that cranky old machinist. It is super easy. There's only 5 things you need to know. Everybody ready? Who's taking notes? Everybody, who thinks they know the 5 things already? Anybody? Okay. All right, first thing you need to know, it will take you longer than you think to get that part. It won't be as fast as you think. Second thing you need to know is you need to know what it is you want to make. Showing up and saying, I really need to make this part. And when they ask you, what does the part look like? You have to actually be able to tell them. Don't tell them what the function is, right? So I really need to make this part. But what's the part look like? Well, I'm not really sure, but I have to be able to put it on the floor, and it has to keep the door from opening or closing, right? So immediately everybody in the room came up with the shape that the part needed to be, right? Sometimes it's more complex. And so don't describe the function you need the part to make when you go talk to the cranky old machinist. Oh, who's ever met a cranky old machinist? And I don't mean here at WPI, because I don't think we have any here. Maybe we do. So we've met cranky old machinists. Who knows what their favorite thing to do is? I've met lots of them, hundreds, maybe even thousands. I know what their favorite thing to do is, besides Bud Light in a bottle. Who knows what their favorite thing to do is? They talk about it a lot over Bud Light in a bottle. Do you know? Oh, they do love to talk about stupid engineers. In fact, there's Facebook groups of machinists, and you can just go join one and pretend to be a machinist, not an engineer, and just listen to them talk about how stupid engineers are. Except there's a bunch of engineers in those groups too, and they usually school the people that are lambasting the engineers. Their favoriteest thing to do in the whole wide world, when a young, snotty engineer shows up, thinks they know everything, gives them a bad design, is to make you exactly what you asked for, especially when they know it won't work, right? And so you could have that kind of interaction with them, or you could learn to interact with them in a more friendly manner. And then when you show up with a poorly designed design, they'll talk with you and help you make it better so that you can be like the star. Because, you know, the other reason your boss sends you to go to talk to the machinist about the new part is because your boss used to be you. And your boss once was that snot-nosed little engineer that went down there to talk to the machinist, and your boss got schooled. They're waiting for it to happen again. It's like knights and squires, right? The knights make the squires polish the armor because when they were squires, they had to polish the armor. And so it's sort of that whole, what's the word? Hazing. Yeah. But I guess it's legal hazing when you work for them and they tell you to go do your job. Anyway, so you have to know what you're making. Don't just describe what it has to do. And you don't have to have a finished design. It's not bad to have this conversation before you have a finished design. We need a part that looks sort of like this, and this is the function we want it to do. That is way better than this is the function we need it to do. But I don't go with that first trip down. Don't go with the interactive sort of idea. Wait till you've established that rapport with the cranky old machinist. You need to know why you want to make it that shape, that way, that material. So it'll take longer than you think. You need to know what it is you're making. You need to know why you're making it. So why does the part that you've designed meet the function that you want it to do? Oops, escape. This is sort of part of what you're making. you need to have picked the material. I had a grad student. He was a repeat offender, repeat customer, I mean. And I had impressed on him the fact that some dimensions are more important than other dimensions. So the whole idea of tolerances and that they're not the same on every number. Yeah.
So yeah, on that point, like if you want to make like airplane seats, for example, you have to make it out of like a light material. Otherwise, the airplane will have to need a super long room to take off.
Yeah, or more powerful engines. So this kid, he'd understood that. And he'd understood that he needed to give me sort of a drawing that had dimensions written on it and not just a verbal description of the part. And he understood who did ES1310. So you've got like a tolerance block thing that you pick the style that you're going to print out your drawing on, right? And so you had like ANSI drawings or ISO drawings that you could pick from. And so down there, one of the things, so it's like who designed it? What's the name of the design? What's the revision number? Who approved the revision? There's all kinds of lines where you can fill that stuff in. So it's sort of accounting for the drawings. But there's also a block where you can say these are the nominal tolerances. So if I didn't tell you otherwise, if it's got 2 decimal places, it's plus or minus 0.01. If it's got 3 decimal places, it's plus or minus 0.05, something like that. And then there's a block where you can say what material it's made out of. So we've all seen that. But it makes sense. You have to specify the material when you're going to specify the part. So he put some dimensions, and it was about, he was using metric units. So like 1.5 centimeters long, so 15 millimeters long, maybe 20 millimeters long, about 6 millimeters in diameter. It's a round part. And he said he wanted it to be made out of aluminum, plastic, or some other lightweight material. And I thought, well, this was when smoking was still legal on campus. So I thought, well, I could just go pick up some cigarette butts that fulfills his design requirements as specified in his drawing, right? Right, so know what you want to make it out of. Don't say aluminum, plastic, or some other lightweight material, because cigarette butt would have filled the dimensional tolerances that he had. Turns out I made it out of aluminum. It was the stuff I had laying around. And that this is the reiteration of all the other ones. The design part of the process, when you're the design engineer, is your job. I remember the first time that this was driven home to me was when I was a young, stupid engineer. I mean, young, very knowledgeable, too smart for my own good engineer. And so when you're drilling if you're putting a hole in a part, you want to know why the hole's going through the part, right? So if you're designing it. So the reason you put holes in parts is so that you can see through them, right? Could be you're putting a hole in the part so that somebody could look through it. Could be you're putting a hole in the part so that later, after the whole thing gets assembled, you could stick a screwdriver through the hole and you could turn a screw that's on the other side to make some adjustment. Often, though, when we're putting a hole in a part, is so that we can press a pin into it, so we can use that pin for alignment, or so that we can put a bolt through it, so we can attach that part to something else that has a threaded hole on the other side, or that we're going to put threads in it so that it could be the thing that the screw or the bolt ties into. Those are typically the reasons we put a hole in a part. Does that make sense? So if you're going to use it to have a screw go through it and go into something else that has threads in it, we call that a clearance hole. Who's heard the term clearance hole before? Most of us have heard that term. How big does it need to be? Say it's a 1/4-20 fastener. How big does the hole need to be? A bit larger than the outer diameter of the screw. So anybody disagree with that? How big does the hole need to be? It shouldn't be smaller, right? If we made it smaller than the outer diameter of the screw that's going to go through it, then we'd need to use a hammer. If we made it much smaller, we'd need to use a bigger hammer, right, to assemble it. So we're not nailing it together with the screw. We're screwing it together. So it's got to be bigger. That's what makes it a clearance hole. How much bigger? Yeah.
Does it depend on what size you're doing? Is there like a shape or
It certainly depends on the function. And it's going to depend on how many holes there are. Well, it's going to be, right, it can't be bigger than the head of the screw, right? If we just quickly draw a picture. Use right side, room control, come on. Right side up, right projector mute. All right, so I've got my fastener. And I'll draw the threads. You don't have to draw the threads. So this is 0.25 inches. So the hole, and I've got my plate that the hole's going through, right? There could be other shape, but it's going to go through something. So I'm going to have a hole here. Of course, in order to have it designed, I have to tell the person making it where the hole is relative to the other edges and where's something you can measure it from. But it's got a minimum diameter. If the hole is smaller than 0.25 inches, you can't put the screw in without damaging it, correct? And if it's bigger, if we say this, what's this, 0.375? I'm just making these numbers up. There's not a there are standards. I don't know the numbers off the top of my head. But if the hole is bigger than 0.375, then the screw's just going to fall through when we put it in, right? So it won't do the purpose of fastening. So we've got a range now. We know it's between 0.25. And so if you're the lazy engineer like I was, you put a little call out here. So maybe I located it. Right, so I just said it's this dimension here, and it's this dimension here. I put those dimensions in there with some tolerance that I made up because I didn't know what I was doing. And then I put a little note here, clearance for clearance for 1/4-20. In my mind, I was done designing because I knew that needed to be a clearance hole for 1/4-20. And I knew that the machinist knew way more than I did about what the size of that hole should be, right? What's the problem? What I've told the machinist with this note is that anything in that range is acceptable to me. Because that's the only information I've given them. Yep. Well, no, but with the note, that's what I've told them. If they measure the screw, I didn't even tell them what kind of 1/4-20, right? Because it could be a socket head cap screw. It could be a countersunk flathead screw. It could be a special really wide fastener. So really, I've only told them the minimum size. I haven't even told them the biggest size that it could be, right? Because I didn't tell them what kind of screw it was. It's the designer's job to say the diameter, we do 551. I don't know. I just made that number up. So it's my job to say that's the size I want. And maybe I want -0 plus so I'm willing to accept anything bigger than this, but not bigger than this plus 0.05. Right? That's my job as a designer. It's not, and so what determines how big you could accept that hole to be? So obviously the bigger the hole is, the easier it's going to be to assemble your part, right? So if we're doing design for assembly, we want that hole to be as big as possible. If we're doing design for function, then if it's too close, so let's say here's the material, so we made it too close to the outside diameter, made it really easy to assemble. But when we put the wrench on this and tighten it, what we're going to do is broach the material with the head of our screw. Who's ever done that? Right? Especially if you put like a hex head bolt into a wooden part. So you make the hole for the threaded part to fit through. Then you start cranking with your ratchet and you suck that head right into that wooden part. And so the machining, and this is machining, we're using the fastener to machine the workpiece now. And that process is called broaching. And how much force it takes to do that is going to depend on how much material there is and the strength of the two materials. Does that make sense? Because the other thing that could happen if this material is really hard is you could broach away the outside of your fastener. Right? You could make the outside of the fastener go away, or you could make the outside of the hole go away if you did that. It's the designer's job to know how big to make the holes. Now, yes, there are standards that you can go look up, and you can say, this I want this type of a clearance hole, and you can go look that up, and you can find out what the difference is. The other thing is you can go to, who's seen like the drill and tap charts that we have around the machine shop? So there's a couple different standards that they have on those. And one of the things you can do is you can say, I have a 1/4-20. It'll tell you this is the tap drill. So if you're going to use a tap to make that thread, that's the drill you want to use. This is the clearance drill. And that's just based on somebody else's engineering judgment, right? But if you're worried about either of these two situations, you're going to have to do some math. And you may have to go with a different size fastener. It's one of the reasons that you design the size of the fastener that you want. So anyway, my boss saw it before the machinist did, and my boss yelled at me and explained it to me. And as soon as my boss said it, I got it. But it's so easy because, of course, the machinist knows more than I do about what size the hole should be. This is what they do for a living. They've been doing this for a living for 30 years. Of course, they're better at that than I am. But if I had some relationship with the machinist and I went down and I talked to him, and I said, all right, so I could put in 5 of these fasteners, and I was thinking to use 1/4-20, but tell me if maybe I'm wrong there. And this is how much force I expected to see. Now, they're not going to do all the math, but they'll have some judgment, and they'll be able to tell you some idea on that and help you get pointed in the right direction. But you can't have that relationship with them unless you actually spend some time developing it. Anyway, so some of the reasons it takes longer than you think to get your parts made. Well, the quality of your design, right? The better your design, the faster your parts are going to get made. So I told you the story about the people sending me the wrong drawing. So we spent 2 weeks making the wrong part. Then we had to spend 2 weeks making the right part once they sent us the right drawing. The number of parts that are ahead of you. So if you're going to a place that makes the parts for you, if they're super busy, then they're going to finish the other work before they start working on yours, especially if you've been a pain in the ass customer in the past. So if you've designed things poorly, they're going to look at yours last. It's human nature, right? I mean, just the number of parts you need. If I need 1,000 pieces, it's going to take longer than if I need 2 pieces. Although they're going to make more money, so they might be more incentivized to set it up sooner. So that's, whether or not they have the stock material. This is on a different slide. I'll wait till I get to that slide. And I just put the quality of your design in there twice because I think that's important. Complexity of your parts, right? The more complex it is, the harder it's going to be to make it. The harder it's going to be for the longer it's going to take to make it. And again, the quality of your design. All right, you got to know what you're making. Do you at least have a concept, right? So I said, don't just know the function it needs to provide. Know the concept. And this is especially troubling to me here at WPI. When the student comes in and says, this is my MQP. And I say, how many people in your MQP project group? And they say 5. And I say, this is your MQP. There's 5 people in your group. If you think about this, for there to be, if there's 5 people in that MQP project group, it took $1 million to put those 5 people in the room. Because your MQP is the capstone. It's the end of your WPI career. And if there's 5 people in that group, on average, it took $1 million to get them there. Somewhere in that range, right? This should be $1 million of value you demonstrate in your design. So when you show up and you say, our advisor said, first, why aren't you telling the advisor? Why is the advisor telling you? But our advisor said, we need something that can do X, Y, Z. Can you help us? I have that meeting 6 or 7 times a term. And well, yes, I can. But it's not my MQP. And if you have a design of a part of a shape that you think is going to solve that function, I'll do 2 things with you. I'll use my engineering judgment and wonder, will your proposed design actually meet the function that you said it needed to meet? And I may give you some advice there because I don't want to help you make the part twice. I want you to design the part right so we can make it once. But then the other thing is, it's not my MQP. And the engineering part is the design, especially, I mean, if you're a manufacturing engineering student, then the manufacturing part is certainly a significant part of your MQP. But if you're a design student, it's the designy part of your project that's the important part. You had a question?
Oh yeah, so like when you mentioned like it might take ill longer than you think. Like one example of that, like I don't know, the thing of a starship, the SpaceX starship, you could expect it to take like 3 months, but it actually takes like
anybody that's ever personally built anything knows that it always takes longer than you expected. Anybody that's ever written computer code? Anybody written computer code? Yeah. Anybody's ever written computer code? You think, all right, so it's Wednesday. I gotta finish this one last little thing. I'm just gonna fix this one little thing in the program. You sit down on Wednesday afternoon. You look up. It's next Thursday. And you've actually gone down a rabbit hole. You haven't even fixed the thing you sat down to do on Wednesday, right? So but it's just to remember that, because when you show up and you're in a hurry, you get less, the people that you're stressed out in front of are less inspired to help you, especially if you haven't previously made a relationship. So minimum, have a sketch. If I say, what do you need to make? Be able to walk over to the whiteboard and say, we need something like this, and maybe it's going to have 2 holes in it. It's going to be about this long with these dimensions. You'll be able to make a sketch of it or already have the sketch. So, and especially if it's early in the design stage and you're thinking, we want to understand what kind of manufacturing processes we might use to make a part that looks sort of like this. It doesn't have to be a final design. And then, of course, on top of sketches, drawings, solid models. I don't think the solid model is sufficient without a drawing if you're asking somebody else to make the part. If you're making it yourself, it may be sufficient. And then have you specified all the dimensions and the tolerances? Right? And again, picking the correct tolerance, that's your job too. It's not the machinist's job. Why you want to make it this way. That's just, and this is really targeted at project groups. When the person who did the design, so these 5-person groups, I hate 5-person groups, by the way. 3 is the correct number for a project group. 5 is a horrible number. 4 is even worse. If it's 4, there's always one person that never does anything. When it's 5, there's always one person that never does anything, but it's not always the same person. Anyway, so if you've broken up the work, and I've got the designer person, and I've got the manufacturer person, and I've got the coding person, and I've got the going to put the report together person. That was the job I always volunteered for. I was really good at putting the words together. Didn't want to do any of the stuff that required, what's the word? Work. Yes. So why are you making it this way? This is if you're having this conversation, you've developed a relationship, and somebody's trying to help you make it better. If you don't know the answer to why was this hole in this location, you certainly don't know the answer to could we move it over a little bit, or could we make it a little bit bigger or make it a little bit smaller. And so just understanding the person who actually made those design decisions should be part of the conversation. So if you didn't do the design work, bring them with you. Understand the design intent. Don't just put a feature on a part if you don't know why that feature goes there. Can you buy the part instead of making it? This is almost always the better engineering decision. If you're making it because you want to learn how to make it, that is a valid reason. If you're making it because you don't have a big budget in your project and you think it'll be cheaper, if you actually account for the cost, it will never be cheaper. But if you're learning to do the process and that's your objective, then absolutely, let's make it, even if we could buy it. All right. What do you want to make it out of? Very often, people will show up in the lab and they'll say, happened this week, earlier this week to me. They'll come in with a piece of aluminum. Actually, this particular group had a stack of pieces of aluminum, but they came in with this piece of aluminum, sort of this shape, a little bit thicker. And they said, can you help us check the manufacturing process for our part? So that's a good question, right? I already have a plan for how I'm going to make this part. I would like somebody to review it before I go put my stuff in the machine and press go. That's a super valid thing to do here at WPI. And I noticed on their block of aluminum that somebody had been using a Sharpie, probably the same person that borrowed a Sharpie from me and never returned it. Somebody had been using a Sharpie, and their block of aluminum looks sort of like this. And with the Sharpie, they had drawn 2 roughly 2-inch diameter circles on the part. And when they showed me the solid model for the part they wanted to make, it looked sort of like this. Did I draw that well? Let's get some thickness here. So, yeah, these walls, they're more straight up and down, but there was a little radius here at the bottom. And so it was a hub. So like a wheel with a little hub that stuck out on the side. That was the part they wanted to make. And then there's a hole through the center. Right, so if I draw 2 views, something like this. So that's one view, and then the top view, something like that. So a shaft goes through the center. Oh, the center hole is a hex, but you don't care about that. And they wanted to make it out of this material. And so the thickness of this material was exactly this distance. And the width was just a little bit more than 4 inches. So is that a good plan for making this part? But it was really important that they have it that day. And that was the piece of scrap material that they found laying around. And therefore, we had to do the process. So what's the way to make this part? You get some 2-inch round material, you hold it in the lathe, and it's what? 2 operations, 3 operations. You drill the hole, you turn down a little diameter, you do a cutoff, right? And what's the process for doing this? Well, first off, they're not going to be so close to each other. You could do them that close to each other. You could put it in the EDM. We could cut those circles out in the EDM. I think it'd be only about a 3-hour cut time. So don't just randomly pick a piece of material, or especially don't go buy some material without figuring out exactly what the right process is to make the part. If you're modifying an existing part, if you got to make some features on an existing thing, bring that thing with you. And if you're modifying an existing part, how much does it cost to replace it if we screw up? If we break a tool in it, if we hold it the wrong way and it bends or breaks off? It's important to know too. Don't just tell us you want to use scrap material, and don't go spend $2,000 of a piece of material that you're going to then chop up into little tiny pieces, where you could have bought the combination of the little tiny pieces you needed for, I don't know, $1,000. Happens every year. These kind of things happen. Yeah.
If you try to recycle the part, you have to get more material. Will it eventually ruin the material you're using?
So my wife used to be a manufacturing engineer at Tiffany and Company. At the time she was working there, she was the world expert at casting platinum. Platinum is expensive material, so they don't want to waste that, right? And when she took over the platinum project, they'd have scrap material left over, right? So if you're making a ring, you cast it, and then you do some machining to make the different shapes and stuff like that. So you actually collect the chips. You don't want to waste any of those chips. It's not like the aluminum chips we don't care about. Well, we do, we recycle them, but you capture all that stuff. Before she took over, they used to remelt it. So when they were melting the next batch, they'd throw the scrap in, some of it, some percentage. And what she found with that particular material is that they could not maintain the quality standard that was required by their internal specs reliably. Occasionally, they'd end up with bad batches because there was some contaminant that went in with that recycling. And so what they did is they sent everything out to get refined. And then it goes through the same process that it did when it was coming out of the ground. They separate all the different elements and all that stuff, and they make the alloy again. So yes, you can remelt it. It costs more to get it refined. They lose. So whatever the value of the scrap was, it costs about 30% of that to refine it. But it was better than having inconsistency in the parts. If you're making, and I guess, what was the value there wasn't really a functional value. It was, does it look like crap, right? Is there a little porousness when it comes out of the casting? But on a lot of material, they can remelt it a few times and they'll put in a small percentage to do the remelt instead of refining. Don't forget the design part is your job. It takes longer than you think. So ASAP, what does it mean? As soon as possible, right? What does that mean? Really? Are you sure? Are you sure that's what it means? What does it mean? I get to interpret what ASAP means. It could mean I don't do anything else, including go to the bathroom until your parts are finished. And it could mean I'll do that when I dang well get around to it. That's as soon as it was possible. Right? So you can't, we need these ASAP. Nobody wants to hear that. I shouldn't say that. Many manufacturing companies will charge you an expedite fee for we need this ASAP. Especially the ones that don't have any other work to do. Because they just need to get paid more because they need more work. Don't come in and say, but I have to do my experiment today, right? Your poor planning is not somebody else's urgency. I got my SolidWorks all done. When can I pick up my parts? You can do that at the Innovation Studio. You can send your parts over. They will 3D print them. They may or may not look like what you expected. And again, there, you got to design it right in order to get the part you want with those 3D printed stuff too. I got to show this to my advisor today. I just need this one simple thing. Please just drill this one hole for me. We always stop and drill the one hole for them. And then they come back 15 minutes later. Oh, the hole was the wrong size. Oh, now the hole was too big, so now we need to make a new part. Yeah, it's never just one simple thing. All right, so what you got to do in the drawings and stuff, you got to tell the designer enough information to make the part. Let's skip through some of this. What time is it? 44. Okay. As a designer, you want to avoid being a kid with CAD. This is what we call you when you give us the bad drawings, when you give us the drawings with features that are very expensive to make and unnecessary to the function of your part. Who's used SolidWorks? Pretty much everybody or something like it. And so when I get two surfaces that come together on my SolidWorks, is there a button that's like blend all surfaces or something? And like you put a fillet there, and then you blend it to the other fillet, and it looks really cool, right? You can make some really cool. Oh, and you can use the colors, and you can put shadows on it, and you do all this rendering stuff. And you can draw some really cool looking stuff in SolidWorks. Think about how the tool is going to fit in there. Let's just look at that fillet for just a second. So when you're doing that fillet, so I got my part here. I'm looking at the end of it. I do my fillet, right? Make this go away, and so maybe the part goes out like that somewhere. All right. All right, so I've got that nice fillet, those parts come together. It looks so pretty. How do you make that? It's easy to do it in the software, right? You click the button, add fillet. It asks you what's the radius. You say this. Does it say use all adjoining surfaces? Yes, because that'll look cool, right? So it'll be rounded on the end here and everything. How do you make it? What's the manufacturing process that makes it? So you can take a ball end mill. If we're looking at it, just the end view here. So we've aligned it so it's no longer the projection and just the end view. We've tilted it around in our software. Looking right at the front face now. So you can take a ball end mill. Excuse me? Here's what I found. Software fails. You take a ball end mill, make a pass there, and then you can make another pass there, and you can make another pass there, and then you can make another pass there, and make another pass there. So you get the idea, right? And so we call that a surfacing operation. It's the way you make convex, right? This is concave, convex. It's the way you make convex surfaces in a 3-axis mill. Yeah. Why did I just take two pieces, weld them together, and then use my grinder, smooth it out? Depends on what you're making.
Would you also be able to turn it 90 degrees if you're going to the bottom?
Oh, yeah, I could flip the part over. And as long as it's not too long, I could have my tool go like this. Right? So I can flip the part on its edge. That fails when you blended all the surfaces together. Unless you can infinitely tip it in all those angles. And you can if you use a 5-axis fixture. Right? You can have it swarf around while you do that. So you can do that. Or if you're making a lot of these in production, so if you're making a prototype, a one-off, that surface machining, that 3-axis machining, it's easy to do. You click a button, the program knows how to do it. It's the same process we use in the Y block for your engine, right? Or you could make a special tool that's this shape. right? And you can just run that one pass down the side of the part. It'll put that radius on it. The problem is, for every radius that a designer might call out, you have to have a special tool. Whereas if on that outside edge, instead of putting a radius on it, you had designed it with a chamfer. Now I can make a lot of different chamfers with the same chamfer end mill. Right? I can make this one. I could make one that's this big. I could make a little tiny one. So I could use the same tool to make a lot of chamfers, or a special tool, or take a long time to make the fillet. So a simple thing of putting chamfers on the outside edges and fillets on the inside edges, because it's really hard to make right angles or sharp angles on inside edges. Very easy to make round angles on inside edges. So as simple as put chamfers on the outside, put fillets on the inside, will make it that much easier to make your part. Don't make holes that are really deep compared to the diameter of the drill. I think 4 to 1, 5 to 1 is the max you ever want to do. Now, is it possible? Yeah, physics says it's possible, right? We make cannon barrels that have a much bigger aspect than that. I actually got to see them making howitzer barrels, like 40 feet long, about this big around, with a hole in it about this big. They make them out of billet. They got a steel rod. They drill a hole down through the center. They call it, amazingly enough, a gun drill, because they design them to make guns. Google gun drilling. It's pretty cool to watch. Yeah, so you don't want to be a kid with CAD. Think about so you guys draw features that are expensive. Stuff that you have to put in the machine several different times. If you could make it with one setup, design it so it can be made with one setup, especially if it's a prototype, if you're trying to get it done fast. Yeah, we talked about chamfer versus fillet. I think I got everything. Oh, this is my favorite YouTube clip, though. Unmute. Oh, that's the best part. I'm H2O intolerant. That was what that's for. Sorry.